Recall how we interpret a classification tree. We start at the root node, and the root node is split on a particular variable. And if we move to the right, it means that variable takes on a certain range of values. Now what we do is navigate through the tree all the way to a leaf node. Every leaf node of the classification tree is a prediction. And if we take a closer look at this prediction, we see what it is a probability distribution over these different classification outcomes. So if we look at this as a histogram, for example, we see there's a relatively low probability of being in the low salary group and a medium probability of being in the medium salary group, which is between 1.24 and $2.4 million. And then the highest probability at this particular leaf node of the classification tree is being in the highest salary group. So this would be your highest paid players. Recall that to get these different salary classes, low salary, medium salary, high salary, we had to take our continuous salary variable and bin it according to some thresholds. Now, the problem with this is that these thresholds are kind of arbitrary. That is, there could be only a few dollars separating a high salary player from a medium salary player. So a few dollars could lead to a discontinuity in the result. So in effect, whenever we take a continuous variable and bin it, we're throwing away information and we're missing out on nuances. And I suppose anyone who's ever complained about a grade that they should have got an A- rather than a B+ because they're only 0.5% off knows exactly what this feels like. A very small difference leads to a relatively large difference in outcomes. An alternative to binning when we have a continuous response variable is to use a related technique called the regression tree. Now, this is identical conceptually to the classification tree. We start at the root node and we navigate through the tree until we get to a leaf node, which is a prediction. But unlike the probability distribution prediction we had before with the classification tree, the prediction in a regression tree is a conditional mean. That is, it's the estimated mean value of the response variable given the path through the tree. Now, unfortunately, in KNIME, it reuses the classification node and the classification tree infrastructure to create the regression tree. So the node itself is a bit jumbled and hard to read and has a whole bunch of information that you don't really need. All you need is the mean and the sample size. So in this case, this prediction, this leaf node of the regression tree has an estimated mean of 5.31 blah blah, which is the salary of the hockey players who satisfy the conditions implied in the tree. And in this case, we have 33 players who satisfy this condition. So of the 33 players in this sample, their mean salary is a relatively high $5.3 million. Recall the hockey player salary data, and if we bring up the histogram, we can see that we have a continuous variable ranging from 0 up to about $9 million per year. Now, originally we looked at this data as a classification tree because in a lot of ways classification trees are simpler. But this is continuous data and we probably should treat it as such. So I'm going to start by using the regression tree tool. And there's a couple regression tree tools in KNIME, but I'm going to use the simple regression tree learner. And I'm also going to set the stage for creating a testing loop by putting in my predictor. Now, remember, I don't need to do binning here, but I do need to do partitioning if I'm going to run a testing loop. So I connect my partitioning node to my data and my top half to my learner, and my bottom half goes to the predictor. And then, of course, I have to connect my model to the predictor. Now, if I go to the partitioning node, remember, what I'm trying to do here is have as much data as possible to build the model, because the more data I have, the better the model will be. And at the same time, I want to have as much data as possible to test the model, because that means my accuracy statistics will be better. So my rule of thumb is about 60-40. So I use about 60% of my data to train the model and 40% to test the model. I could use 70% and 30% to test, but I think that's getting a little short on data for testing. So this is just a rule of thumb balance I tend to use. There's nothing special about the 60-40. So I click on that, and now I'm all connected, and it's time to configure my regression tree learner. So as before, this is very similar to the classification tree learner, except it's actually a little bit simpler. At the very top, my target column, or my response variable, is total annual pay. Remember, this isn't binned, this is a continuous variable. The nice thing about the regression tree interface, though, is I have my own little column selector here. So I can go through this as I did before and just double click the columns I don't want. For example, birth date is a string, so it's got too many values. I can get rid of that. I didn't want country, I wanted region. I didn't care about the drafted by team, and I didn't care about the team. I really just cared about market size. And the rest of these are continuous. Now, of course, I have to remember to take other potential response variables out, like this other version of pay. Otherwise, I'm going to get a meaningless result. Okay, so I can run that and see what I get. So execute and open views, and I see at the root of my tree that it looks like the sum of power play assists seems to be an important discriminating variable. Now what I can do is I can click on the root node and then go tree, expand everything, and what I get is a real problem. I see over here on the far right, that thumbnail of my tree, that my tree is huge. It's got way too many branches. It's way too bushy. So maybe before I continue, I'm going to go back to my configuration node for my regression tree, and I'm going to scroll down a little bit to some of these options at the bottom. Okay, so for example, I might want to set the minimum node size. After all, we're using these nodes to estimate the mean of a distribution. So typically we want to have a sample size of around 30 or more. And we can also set the node size for a split to something like 60. So you have to have at least 60 records or 60 data points before a child split can be made. These are pretty straightforward kind of changes to this to make sure that we don't overlearn the data and get estimates based on just a handful of training examples. So now I go execute and open views again, and if I expand the whole tree, I see I get a much more reasonable sized tree, and I can see that some of my splitting variables are power play assists. I've got size. I've got various different things in there. Draft number, weight. So it's sum of shots. So we get some interesting results. But what I really want to do is use my testing loop now to see how accurate my model is. So although regression trees have really almost nothing to do with linear regression, it does give you something like an R-squared. So if I bring up a scoring node, just like I did in classification trees, I don't want to use the confusion matrix score. I actually want to use the numeric score, and I can slot that in there. It's a little tight, and I can connect it up here. Now I have to double check my configuration to make sure that it's configured properly, and it turns out not to be. So my predicted column is the prediction of total annual pay provided by the regression tree, but my reference column is the actual total annual pay in millions provided in the holdback sample. So I don't know why that didn't pick up automatically. It didn't, but I fixed it. Okay. So now I can run my scorer, and I go execute and open views, and I see I get an R squared of about 3.09. So that's not bad. I could go and maybe fiddle with some of my configuration options in this tree to get maybe a higher R squared. But really what I want to do at this point is sort of get an image of what that R squared looks like, an image of the quality of the model. Now remember how we did this in SAS is we plotted the predicted value versus the actual value and looked for models that put all the points along a 45-degree line. So I'm going to do that. I'm going to bring up a scatter plot. And there's a couple different scatter plots. I'm just going to take the simple one and connect it up to my results. Now, because remember that my predictor provides a prediction and the actual value from the lower branch of the holdback sample, so I should be able to execute and open my scatter plot. And sort of right off the bat, we get a bit of a mess here. And the reason is the scatter plot is sort of dynamic. You're supposed to be able to set the variables on the two axes as you go, but there's way too many values here. And I'm going to be opening and closing this over and over again while I'm testing and building my model. So I'm going to cheat a little bit, and I'm going to bring in a column filter. There's a column filter. We used this previously, and I can try to drop it, if I'm good enough, right on the existing node. And apparently I'm not good enough. What if I click away? That's too bad. Sometimes you can drop it right on the line, and it makes the connection for you. In this case, I'm going to struggle mightily to get this to work. So I'll just delete the scatter plot, connect the column filter, and then bring the scatter plot back in. Okay, so I'm working in a very low resolution here for the video, so it's kind of hard to get things working. Now, why did I add the column filter? Well, remember, I want to graph just two things, predicted versus actual, and an easy way to do that using KNIME is to make sure that the only two variables, the only two columns going forward from this node are my observed value of annual pay and my predicted value of annual pay. So now when I run my scatter plot, it's still not quite beautiful, but it's much easier for me to put predicted along the horizontal axis and actual along the vertical axis. And what I see isn't exactly a beautiful diagonal line, but at least it's sort of upward trending. Now, as for the weird shape of this scatter plot, remember that each leaf node in the tree is a predicted value. So there's one leaf node, for example, that's predicting these values right here, sort of $3.3 million. There's another leaf node that's predicting these values way over here on the far right at the $5 million mark. Now, what this is showing is that there's actually within the records or the players that match the criteria for that prediction, the range of values is actually quite large. The mean might be somewhere close to 5 million, but the range is much higher than that. And this gives you a sense that this model's not especially great, and that's why we get an R squared of 0.3. On the other hand, like I said, there is sort of an upward trend. So certainly on the low end, it's doing a pretty good job of predicting the low-paid players. It does have some difficulty predicting the highly paid players. So that's the basics of a regression tree, very similar to what you've done in a classification tree. But remember, the difference here is that you can keep your continuous response variable. You can select columns very much the same way as you did before. Select as many as possible and let the algorithm sort out which ones are relevant. And then remember, when you read the tree, what you're reading is conditional means. This is the mean given a certain set of conditions implied by the path through the tree.